Hello everyone, Lucas Campos today talking about the Physics 2212 Lab 6 magnetic braking with Faraday. Moving to the agenda for today, we have the introduction, kind of purpose of the lab experiment itself, glow script code, possible errors, and then discussion questions. Introduction. So the purpose of this lab was to observe a real life and simulated model of a bar magnet falling through a conductive tube of aluminum foil. And we're going to use some different laws here, like the Beer-Savart law, magnetic flux, Faraday's law, Ohm's law, Lorenz's force. And then just to kind of sum it up, in the real model of the experiment, after a average of 5 trials, we came out to have 0.742 seconds, and in the simulated model, 0.425 seconds. And here just some of the formulas being used. So in the actual experiment, so here we have a bar magnet going down a tube of aluminum foil, and we measured the inner radius and then the outer radius and the length of the tube, and it enters up here and travels down, and it kind of gets slowed down because of the forces. So the tube we measured a 0.46 meters measured length, a width of 0.0045 meters, and inner radius of 0.015 meters. It's basically just a standard aluminum tubing, like aluminum foil. Moving into the glow script code, here we put those measured values into the lengths in step 1. And then in the second part, we have the mu magnitude. And this is the magnetic dipole moment. And this is what I found from lab 3. So I just transfer this over. And then here, just we set initial conditions. And then over down here, we calculated the magnetic field of the bar magnet, creating R mag, R hat. And then this is the Beer-Savart law over here. And then in step 3, calculated the d flux dt, and this is just basically the laws being used and from there's formulas from class. Moving into the next part of it, just we initialize gravity here, and then we create the magnetic force, and we calculate the current in the ring, and we computed the typical B field at each ring, and calculate magnetic force. And here now we have the net force, it's just sum of all the forces. And then we updated the magnet's velocity and position, and just Newton's second law stuff over here. And then we plotted the curve. So in the actual results of the simulation, it showed this magnet traveling down, and it created this velocity time graph. See the downward slope, and it ends at around, the time was 0.423 seconds. So that's the computational model. It's possible errors in the actual experiment. So there's friction in between the magnet and the tube. The magnet makes contact with the tube as it travels. Human error due to measuring time, and measurements done when we actually measure the aluminum foil tube. So further questions: what if the resistivity of the conductor were reduced as close to 0 as possible? How would the dynamics of the falling magnet change? So resistivity is directly proportional to resistance, so there'd be nearly 0 resistance. Stronger opposing magnetic fields, larger eddy currents will generate stronger magnetic fields at opposing magnet's motion. There'd be greater magnetic dampening. The increased opposing magnetic force significantly slows down the magnetic descent. And slower descent or near levitation, the magnet may fall very slowly or even achieve near levitation if the magnetic force balances gravity. And there'd be minimal energy dissipation. Energy loss as heat would be minimal due to the extremely low resistance of the conductor. Moving into the second what if question: what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would create path disruption. It would interrupt the continuous current paths, leading to redistribution around the holes or slots. And the inductance and capacitance changes. It would alter this by impacting the overall current behavior. Field distribution modifies electric and magnetic fields, influencing current distribution. And then localized heating, it increases resistance and localized heating around edges, causing potential power losses. That concludes the lab 6. Thank you.